Okay, so thanks for the kind introduction. So today I will mainly talk about how to tackle non-local electronic correlations with a new method quite new method that I have developed, which is the ab-initio dynamical vertex approximation. Okay, so since this is all about correlated electrons and strongly correlated materials, I will start by briefly introducing the Hubbard model and dynamical mean field theory, which is like an established method to solve or to tackle the Hubbard model. And then I will come to the main part of my talk, and I will introduce this method, which is the ab-initio dynamical vertex approximation. That is a diagrammatic extension of this dynamical mean field theory. And then I will also show some implementation details of this AbinitioDΓA computer program. And in the end, I will show some applications, so some results that were obtained for bulk and monolayer strontium vanadate and the Kagome Hubbard model with this AbinitioDΓA method. So I like to start my talk with like a simple picture for correlation, classical correlation in this case. I think every one of you knows who has ever played this Mikado game knows that it's very difficult to remove one of those sticks without moving all the others. And that is because they are all in relation with each other, so they are, so to say, correlated. And the situation is a bit the same with correlated electrons in a solid. And in solid state physics, we basically have a quite simple model for correlated electrons, which is the Hubbard model. And in the Hubbard model, you have electrons that can hop from lattice side to lattice side with a hopping amplitude T. And when the electrons are on the same lattice side, they interact through a local Coulomb interaction U. So the Hubbard model, the Hamiltonian you can see here, it has two terms, a kinetic energy term and a Coulomb interaction term. And they compete with each other. That is what it makes it so difficult to solve. We have so many indices here in the Hamiltonian because this is like a multi-orbital Hubbard model. And so this L, M prime, ML prime here, these are orbital indices. And the correlated orbitals that are often treated in the Hubbard model are, for example, the 3D orbitals of transition metal elements or the 4F orbitals of rare earth elements. Yeah, and unfortunately, there exists no straightforward exact way to solve the Hubbard model, so we need approximation. And one approximation to solve or to tackle the Hubbard model is the dynamical mean field theory, DMFT. And here on this slide, you can see in a very simplified way the main idea of DMFT. So what DMFT basically does, it maps the Hubbard model self-consistently onto a single impurity model. And in this impurity model, we have a single impurity site with the local Coulomb interaction U. And this impurity site is coupled to a bath, to a mean field in space, which represents the rest of the solid. And so the electrons, they can hop from the impurity site in the mean field and back. And what DMFT can describe and what DMFT captures are all local dynamical electronic correlations. And in a diagrammatic context, this means that DMFT includes all local irreducible one-particle Feynman diagrams. So it is a diagrammatic method, a diagrammatic Green's function-based method. So what you can see here, so the dashed blue arrow here represents the Green's function, and the red circle, the sigma, is the self-energy. Yeah, and the self-energy effectively includes all the effects of electronic correlations. And in DMFT, since DMFT is based on the solution of this single impurity model, which is local, so the DMFT self-energy is purely local. So this I here, they are side indices. So as I just told you, this DMFT is a, let's say, well-established method to address strongly correlated electron systems and strongly correlated materials. So you can already do quite involved a realistic material calculation with the DMFT. So for example, here I did a study, recently did a study for cerium iron intermetallic. But as I mentioned, DMFT is based on the solution of this single impurity model. So it includes only local electronic correlations, and this DMFT self-energy is purely local. But sometimes we would like to include also some non-local electronic correlations. This is, for example, the case, for example, in a material close to a magnetic phase transition, where the correlation length and non-local fluctuations become very important. Or non-local correlations can also be important in 2D materials, because as you can imagine, 2D materials, they are very far from this ideal approximation of a mean field in space that's assumed in DMFT. And there exist various methods to include non-local electronic correlations. And I'm here now talking about extensions of DMFT. And also there exist multiple options. So one option is to do cluster extensions of DMFT. And that means that you basically replace your single impurity model by a cluster of impurity sites. So you can easily imagine that those cluster extensions of DMFT, they include all non-local electronic correlations in the range of the cluster size. Then there also exist diagrammatic extensions of DMFT. And these diagrammatic extensions have the advantage that they don't only include like short range non-local electronic correlations, but they can also include like really long range non-local electronic correlations. And there exist various versions. One of them is the dual fermion method, one the tri or quadrilex approach, or the dynamical vertex approximation that I will talk about in this talk. So on this slide, you can see in a nutshell, basically the main idea of the dynamical vertex approximation DGAMA. So as I mentioned before, it's a diagrammatic extension of DMFT. And DMFT, as we said, contains all local irreducible one-particle Feynman diagrams. So here you can see two examples. So the index here, again, this is a site index, so it's purely local. So the DMFT self-energy is purely local one. And then in DGAMA, we take this assumption of locality, like one order higher regarding the order of diagrams. Yeah, so we assume the two-particle vertex function to be purely local. So this, basically this lambda here, this is the fully irreducible two-particle vertex function, and that one is assumed to be purely local in DGAMA. And this local vertex is then our kind of construction block in the DGAMA, and we use it to construct all kinds of non-local diagrams. So as you can see here, for example, this quite complicated Baquet diagram is formed of like these blocks of local lambdas, which are then connected by non-local one-particle Green's functions. And this building and resummation of this all possible kind of diagrams, this corresponds to solving the so-called Baquet equations. And this basically can be done, but it's like numerically very involved, especially like for multiple orbitals. So I would say for multiple orbitals, it's not feasible. So we introduce an approximation. Yeah. So basically we restrict ourselves to only a certain class of diagrams. We construct only ladder diagrams, and that is called the ladder DGAMA. So you can see this diagram here. It looks like a ladder, right? So you, like in a ladder, you add one gamma lock, so one vertex, one local vertex, another local vertex, and you connect it with non-local one-particle Green's functions. And what did I want to say? Yeah, so this can be a bit confusing. So before it was the lambda, so that is the fully irreducible vertex function, while here it is the gamma, and this is the vertex function which is reducible irreducible in a particular channel. So in this case, in the particle hole channel. Because basically for these diagrams, if you take all possible two-particle diagrams, they are either fully reduced. You have three channels. You have the particle hole channel. You can think of it like this horizontal direction here, basically, where you construct the ladder diagrams. Then you have the transversal particle hole channel. That's like rotating these ladder diagrams in the vertical direction. And then you also have a particle-particle channel. So that is all you have. Yeah. And so here in this ladder DGA, everything is limited to the particle hole channel. And so we also use the irreducible vertex function in the particle, irreducible in the particle hole channel. That means it contains also diagrams like this kind of, which would be reducible in another channel, yeah, in the particle hole transversal channel.
Anna,
okay.
just to inform you that we don't see your pointer, so I don't know if you're pointing and then.
Okay, yeah, I'm pointing at something, so I don't know if I cannot change this, I think.
Okay, just that you're aware that we don't see your pointer.
Yeah.
So.
I try to. Okay. So the last diagram here in this box is basically a reducible diagram in another channel. But these are basically details. You don't need to remember them to get like an overall idea of this method. The important thing is that you have this building block, which is this local vertex function, which is irreducible in a certain channel or fully irreducible, and you use it to construct non-local diagrams. And in the case of this ladder DGA, you restrict yourself to ladder diagrams. Yeah, and the non-locality comes in because you connect these local building blocks with non-local one-particle Green's functions. And then by summing up all these diagrams, which basically this corresponds to solving the beta-psi-beta equation in this channel. And then you get your full vertex function. So that's the red F here. And then from this full vertex function, you can use it in the Schwinger-Dyson equation of motion. That's what you can see here now. And from that, you can get the ab-initio-DGA self-energy. And that one is now not local anymore, like in DMFT, but it's a non-local object, and it contains also non-local electronic correlations. And this dynamical vertex approximation DGA method has already been developed like 10, 15 years ago, mainly by Alessandro Toschi, Andrei Katanin, and Carsten Held. And it has already successfully been applied to the one-band Hubbard model. And my task in my PhD was to extend this methodology to multiple orbital systems so that we can do realistic material calculations with it. And as you can imagine, this is not a very straightforward, not very simple task, because these vertex functions, they are very large objects, especially for multiple orbitals. So they have like when you have multiple orbitals, then in addition to like 3 frequency and 3 momentum indices, you have 4 orbital indices. So 2 on the left side of the vertex and 2 on the right side. So you need to derive all the multiple orbital equations with the orbital indices. You need to do this carefully and correctly. And then you need to think how to deal with these large objects numerically and to implement the computer program. And this is then this AbinitioDΓA method that I will talk a bit about on the next slides. So in AbinitioDΓA, so what I start from is basically an ab initio DFT plus DMFT calculation. And there, from the DFT, I get the one electron part of the Hamiltonian, and also the Coulomb interaction, the local Coulomb interaction and the non-local Coulomb interaction. I can calculate from first principles, for example, by using constrained random phase approximation. And then by doing the DMFT calculation, I get the DMFT self-energy of the material and the one particle Green's function that's written here in terms of creation and annihilation operators. And then in a second step, I need to compute, to measure because it's done in continuous time quantum Monte Carlo, the two-particle Green's function of the DMFT impurity problem. Yeah, so that is what you can see here, the object here as a formula, but also in terms of diagrams. So that is maybe more clear. So this two-particle Green's function, it consists of various terms. So the first two terms that you can see here, the first two, they are disconnected. They basically represent the independent propagation of two particles, or a particle and a hole. And since I'm here now always working in the particle hole channel, it represents the propagation of a particle and a hole. Yeah. So you have this independent propagation of electrons and holes, but then of course, the electrons and the holes, they also interact with each other. And that's the third diagram here, which includes the vertex function, right? So the vertex function is like, you can see it like a scattering diagram, right? So there are two electrons, or electron and a hole, coming in, they interact with each other, and then they continue to propagate. And this gamma lock is now this main building block of the DGAA. So I need to extract it from this two-particle Green's function, which is measured in the DMFT impurity solver. And you can see that in terms of these simple equations down there, right? So I extract this gamma lock from my DMFT impurity problem simply by measuring not only, it's not simple, but measuring not only the one particle Green's function of the DMFT impurity problem, but also the two particle Green's function. And then in the next step in AbinitioDΓA, I supplement this local vertex with the non-local Coulomb interaction. So that is the two diagrams here, the V of Q and the V of K minus K prime. And from a physical point of view, this is kind of a natural extension of the vertex function, because as the vertex function, as the lowest order contribution, contains the Coulomb interaction, right? So the local Coulomb interaction is already contained in this local vertex function. And then I explicitly supplement it with the non-local Coulomb interaction. So that's shown in this first line here. And then I use this building block, which is now the local irreducible vertex function, this gamma supplemented with the non-local Coulomb interaction. I use it to construct non-local ladder diagrams through the Bethe-beta equation. In this way, again, I obtain the full vertex function, which is this f of q. So this is, of course, now a non-local object. And that, like in DGAA, we can insert it in the equation of motion, and together with the Hartree and the Fock diagrams, it gives me the non-local AbinitioDΓA self-energy. Yeah, so that one has now a K dependence, right? So it's not purely local anymore, like in DMFT. Yeah, so that is basically already everything I wanted to say for the method. Now I still want to give you some implementational details about this method, about this AbinitioDΓA method. The first thing I wanted to talk about is the computation of this local vertex function, which is done in continuous time quantum Monte Carlo in the hybridization expansion. So what I use is this V2Dynamics program package. It's like it's openly available also. It's basically a DMFT solver, which is developed in Vienna and in Würzburg, and it's specialized on the computation of two-particle Green's functions also, right? So there have been several advanced developments in this direction. One is a worm sampling technique to measure this two-particle vertex function, and also the implementation of vertex asymptotics, which was done by Josef Kaufmann in Vienna. because you need to think this object, it's like a huge object. Such a vertex function has, the local one has like 3 frequency indices, like 2 fermionic frequencies, 1 bosonic. And in addition, for multi-orbital systems, it has 4 orbital indices and 4 spin indices, right? So you need elaborate techniques to compute, to make this feasible to compute. And for example, in this vertex asymptotic, so you can see here the figure I put. On the left side, so what you can see is the local vertex for a specific bosonic frequency. On the x-axis is 1 fermionic frequency, on the y-axis the other. The left figure shows the vertex computed in CTQMC without vertex asymptotics. So you can see there is, for high frequencies, so in the corners, there is a lot of numeric noise, while on the right side, it's with the vertex asymptotics that Josef Kaufmann implemented. So basically with this vertex asymptotics, you can suppress all this noise. And what you make use there is that in the for large frequencies, these 4-point vertices, they can be approximated by 3-point vertices. Yeah, that's the object that you can see down there. And that is a much smaller object because it has only 2 frequencies, right? So by that you can suppress the numerical noise, and you can save a lot of computational time, right? And then the second thing I want to briefly mention is the storage of this local vertex. So it's a very, very large object. So you somehow try to reduce the file size. So what we do is we use like a HDF5 file format, and then we store only the non-zero elements. So non-zero because you need to, you can imagine that depending on crystal symmetries or the form of Coulomb interaction that you employ. So if you employ only density-density, Coulomb interactions, or Kanamori, or the full U matrix, not all orbital spin combinations are non-zero. In fact, a lot of them are 0. So what we do is we don't store all these zeros. So we store only the non-zero orbital spin combinations. And we do this in such a HDF5 file in form of a lookup table. So basically you convert, you have here these sigma 1, sigma 2, sigma 3, sigma 4, which are the spin indices of the vertex function. The L, M, M prime, L prime are the orbital indices. You convert those to one index, simply a number. That is then the name of the group in your HDF5 file. And under this group name, this number, you then store the vertex function for this orbital spin combination. And you store only those which are non-zero. So for example, for this calculation for strontium vanadate that I did, you can save like an order of magnitude, right, with respect to storage. So this is basically what is still done in the QMC solver, in the impurity solver. Then the next slide here, I wanted to mention a few details about this AbinitioDΓA program, which uses this local vertex function extracted from the QMC solver as an input. This is this building block that I showed you before in the diagrams. And here the first important, or the most important thing to note is that I use compound indices. That means combined orbital frequency indices. So I combine basically such a vertex function has on the left side one fermionic frequency index and 2 orbital indices. You combine them into one compound index, and on the right side of the vertex you have another 2 orbital indices and fermionic frequency index, and you combine them in the other compound index. Then basically you can do everything in the form of matrix operations. So big part that is done in this AbinitioDΓA program is basically linear algebra. So basically like a matrix multiplication that I've one exemplary matrix multiplication that I show here. So it's a multiplication of this chi0 is the non-interacting susceptibility multiplied with local vertex. And then I make use of some symmetries in order to save memory and computational time. So here basically very simple. I know that this non-interacting chi0 has block diagonal structure. So here where it's white, it's basically all zeros. So I don't need to multiply like two very big matrices with each other, but I can do this like block by block, slice by slice, right? So instead of multiplying like two very large matrices with each other, which gives me another very large matrix, I can use like small blocks and fill up the one large matrix. Yeah. So in fact, in the program, I work only once with the matrix that has like the full dimension. And with the full dimension, I mean like fermionic frequency times orbital squared in both directions. That is because at one point a matrix inversion needs to be done, and that you cannot break down into smaller operations, right? So there I really need the full matrix dimension. Yeah, and here's another example. This is how you obtain these 3 leg vertices, which have only 2 frequency indices in this matrix form, right? It's basically the summation of the left fermionic frequency index. So there, when you sum, you end up only with the combined orbital index. Yeah, so these are just like a few details about this program. And the program is openly available. So you can download and use it from this GitHub site, basically. Yeah, and then I still have a little time, I think, to present a few first results obtained with this AbinitioDΓA program method. So the first, this one was basically needs to be more seen like a benchmark, a test bed material for this method that I used when I implemented the program. So it's a strontium vanadate. It's a correlated metal with a perovskite structure, and the correlated orbitals in this material are the vanadium T2G orbitals. So basically it's a 3-band model. So you need to treat 3 orbitals in AbinitioDΓA. And yeah, it's a correlated metal. So it shows this in experiment, in photo emission, it shows that you can see here in this. Okay, you cannot see my pointer, but you see the figure. It's a photo emission data. It has a quasi-particle peak, and then it has this at -2 eV approximately. It has the satellite peak, which is a Hubbard band. And this can be captured by methods for strongly correlated electrons, which is like DMFT, also by AbinitioDΓA. And it's very well studied material that is often used like as a benchmark, a test material for new methods. And so I also used it for this AbinitioDΓA method. What you can see here are DΓA and DMFT results for this material. So what you can see in the first row, so it's 2 rows. The first is for the gamma point. The first column is for the gamma point. The second column is for the X point. Then in the first row, you have the imaginary part of the self-energy. In the second row, you have the real part. And then in the third, you have the spectral function. In gray, basically, it's the DMFT result, the dashed gray, while the colors, they represent the AbinitioDΓA result, and green and violet represent different orbitals. So as you can see, there is not much difference between DMFT and ab-initio-DΓA. So in the real part of the self-energy, one can see some shift. But yeah, from a physical point of view, this is not very exciting, right? So it was more to test the method. But then, as I mentioned before, is when you expect non-local electronic correlations to be more important when you go to lower dimensions, right? And so what my colleague, Matthias Pickem, then investigated was monolayers of strontium vanadate grown on a strontium titanate substrate. And there you basically then have two options for the surface termination. So it's either VO2 terminated or SRO terminated. And in both cases, you have, when you thin down the strontium vanadate from the bulk to a few layers, so to the monolayer, then you have a transition from a metal to a mott insulator. So at the stoichiometry, where you have like one electron in the T2G bands, so this yellow line in both phase diagrams, this represents the mott insulator. But then the phase diagram is quite different from for the two different options. And this phase diagram they obtained by computing non-local momentum-dependent susceptibilities, which is an odd. So they did not do like really AbinitioDΓA calculations for these monolayers, but the other option is to compute susceptibilities, momentum-dependent susceptibilities in this. That is also something that can be done in this AbinitioDΓA program. So you can calculate, for example, the magnetic susceptibility or the charge susceptibility. Then you can look where those susceptibilities, so for which momenta, for example, here for pi, for which momenta they have a maximum or where they peak or diverge, there you basically have a transition to magnetically or charge ordered state. And this is how they identified the different phases in these phase diagrams, right? So this is another option, because basically those two particle vertex functions, they are generalized susceptibilities, right? So by doing then the correct orbital summations, simple transformation, you can directly arrive at magnetic and charge susceptibilities that you can then analyze for the material that you are investigating. And then a second application that I wanted to show is for the Kagome Hubbard model. So this is a work done by Josef Kaufmann, who was a PhD student in Vienna. And this is basically, it's not, it's not an ab initio calculation, but it's a model calculation, but it's like a realistic model for such Kagome metals. So here in the first figure, which is indicated with the A here, it shows you this Kagome lattice, which consists of these hexagons and triangles. And it has the green area shows you the unit cell. And basically you have with 1, 2, 3 indicated are the 3 atoms in the unit cell. And below you can see the tight binding bands. It's basically 3 bands, and they belong to the 3 atoms in the unit cell. At this Kagome lattice, the Hubbard model on the Kagome lattice is interesting because it's a frustrated lattice. So you can have at the same time, you can have spin frustration, but on the other hand, you also have strong correlation. So you can have a lot of competing correlated phases that you can investigate in this model. And as for all strongly correlated models, when you increase your U to a sufficiently large value compared to the bandwidth, you get a Mott transition. That's what they also observed in this material. So on the right, you can see that they did DMFT and DGAMA calculations for this model. On the left, in left column shows it for U equal 3, and on the right column is for U equal 6, so larger value of U. but still not at the Mott transition. So you can see you have those quasi-particle peaks, bands at the Fermi level, which are renormalized in DMFT and in DGA. And you can see in DMFT and in DGA, you have quite a lot of incoherent spectral weight. And these, you can also clearly see the Hubbard bands there. And they are more pronounced in the DMFT case than in the DGA case. So in the DGA case, the lower Hubbard model, the lower Hubbard band, it merges with this quasi-particle bands. So from here, it seems a bit that in DGA, the model is less correlated than in DMFT, and it also, doing DGA does not simply mean that you add additional non-local correlations on top of your DMFT correlations, but you have a better description of correlations, right? And then what they calculated is the dynamical structure factor, which is directly related to the magnetic susceptibility. So this is a dynamical object now, it's susceptibility depending on the frequency omega. Yeah, and basically from a physical point of view, I think what they observed was simply that it doesn't change too much this dynamical structure factor over the Mott transition. So this was more a bit to show what you can do with this from a technical point with this program. Yeah, and so this is the end of my presentation. Here you can see the two main publications. The first one is the PRB about where you can find all details about the method. And the second one is a computer physics communication, where you can find details about the computer program. Yeah, and as I said, you can download and use and even further develop this code on this GitHub site. Yeah, and that's all from my side for the moment.
Thank you very much, Anna, for the interesting talk. So there's time for questions. So please raise your hand in the reaction section if you want to ask a question. I see there's a question from Lorenzo. Please go ahead. Hello, can you hear me?
Yeah.
Yes.
Yeah. Well, impressive work. Congratulations. I would like to know if you or colleagues of you are exploring the idea of inserting this dynamical vertex into two particle calculations. So something like optics. Imagine you want to probe the phase transition by reflectivity. Something like this could maybe include strong correlation in better salpeter calculation of excitonic properties. I would like to know if there is someone working.
Yeah, I mean, I would be interested to do that, like to do, for example, optical conductivity with the vertex corrections, right? Mm-hmm. That would be very.
It looks even more natural somehow, because it is the vertex you have. It's already a four-point object, so it's quite natural to introduce it in a two-particle correlation.
Yeah, it's a bit in this direction also with the susceptibilities, right? The magnetic susceptibility,
exactly.
The charge susceptibilities, and then also for the optical conductivity. There is some work that has been done in the group of Carsten Held in Vienna for optics, but that was for a single band Hubbard model so far. Now I don't know exactly the title of the paper, but it's by Carsten Held, Anna Kauch, yeah, and people in Vienna. But for materials so far, nothing has been done, I think. But this would of course be interesting. Yeah.
Mm-hmm. Thank you very much.
Then there's a question from Frederick Nielsen.
Yes. Yeah, thanks for a nice talk and impressive work. So I have a question on, you do this in a one-shot fashion, right? So you solve the impurity problem, then you get the vertex, and then you solve the Betzel-Peter equation, but you never have a feedback from the non-local correlations back into the impurity problem. Is this something that you would expect to be important?
Yeah, sure.
I mean, I would expect that to decrease the degree of correlations even more, right?
So the first version of the program that I implemented was a one-shot version, and kind of like I implemented here, and like you mentioned. But then for this work on the Kagome Hubbard model, Joseph has implemented some kind of self-consistency, but the self-consistency is only at the level of the Betzel-Peter equation. So he does not solve the impurity model multiple times. So this is like one of the very numerically very expensive parts of the program. But there is, in that work, there is some kind of self-consistency. And that's of course important. Then when you have real effects, so in this bulk strontium vanadate calculation, it doesn't matter much because there are basically no or almost no effects. But as soon as there are big effects, you need either some self-consistency, or what they are doing at the one band level, they doing something like, we call it Moriasque lambda corrections. So they do one-shot calculation, but then there is some correction in the end on top of that.
Okay, thanks. Yeah, okay, thanks.
Okay, thank you. Then there's a question by Maximilian Merkel.
Yeah, thanks a lot for the talk. It was really interesting. Like, I'm doing a lot of DMFT, and I was wondering how DGAMA worked, and it was like a really nice explanation. Like, one thing I was wondering about is, so in DMFT, I think it's quite clear what we're neglecting. It's the non-local part. Is this something similarly intuitive you can say about the DGAMA approximation?
What you are neglecting there?
Yeah.
Of course, in the way I'm doing it here in this, I have non-local diagrams I built in the particle hole channel. And then in the end, through symmetry considerations, I also get the non-local diagrams in the particle hole transversal channel. But I have no non-local diagrams in the particle-particle channel. So there I have only local diagrams. So for superconductivity, this is in this formulation, it's not good enough. I would say, for example, this is one thing that you neglect. Yeah.
All right. Thanks.
Thank you. I have a question myself. I was wondering, so you have an implementation of this DGAMA. Are there other implementations that you can compare to? Also, because indeed you showed us very nice equations, but also very involved, they seem. So I don't have much experience with that, but I know with other ab initio methods like GW, if you take two codes, it's not always easy to get the same result because there are many input variables that you have to converge. You have to make some choices. So have you tested it? Are there any other implementations, and do they all give the same results? Or?
There was one previous. There exists one other implementation only for the single band version. That was the one that was done when the DGAMA method was originally introduced, so around 2010. So of course I tested with this one, and then of course I did a lot of tests. So you can do everything locally. So you check if you get if you reproduce the DMFT results. You can do checks with the orbitals. You need to do very carefully, right? So you need to check if you have like 3 degenerate orbitals, that you get in the end the same for all 3 degenerate orbitals. I did not do any explicit benchmark check with GW. That would be like important if these calculations that I showed here, they were without the non-local interaction B. So for that one, it would be maybe good to do a cross-check with GW calculations also.
Yes, I meant more a check against another DGAMA implementation, but if I understand you correctly,
yeah, so there is
are not
only
many
there is only this, it's a
Yeah.
new method. So this is a
Okay.
problem that you have when you implement new method. There is only this single band implementation that you can check with.
And for the monolayer calculations, so there you show the DGAMA results, I think. How would it compare to the DMFT results? Would the DMFT then?
No, so actually, in the monolayer, they calculate what I show here. You can see the slide, right, of this monolayer strontium vanadate. It's not really DGAMA results. There is no DGAMA self-energy here. So here you use it to calculate two particle susceptibilities, right? So you calculate those susceptibilities, but these are then more susceptibilities within DMFT. Yeah, it's not the DGAMA susceptibilities, but it's Q momentum dependent susceptibilities within DMFT. This is, I think, how this needs to be looked at.
Okay, there are two other questions. So let's start with Elena, who didn't ask a question then, yet, and then Lorenzo.
Yes, thank you, Anna. I'm not an expert, so I would like to know which is the physical interpretation of the impurity that you mentioned at the beginning.
Yeah, so this is not, it's kind of an artificial impurity, right? It's not like kind of in a metal, you have a magnetic impurity, something like this. But it's like you basically, I go back to this picture. You're looking for an impurity model that best, you do this in a self-consistent way that's indicated by these arrows here. You look for an impurity model that best represents your Hubbard model, your lattice model, right?
Okay.
So kind of this, this represents your correlated orbitals, and the bath represents the rest of your lattice, right?
So it's like a substitutional atom or not? Not at all.
I'm not sure what you mean with like substitute, but you don't add an additional atom or something like this. But kind of the impurity here then has the orbitals that you include, for example, the orbitals of your iron 3D orbitals that you also have in your lattice. Yeah. So in your lattice, you have a lot of iron atoms with it's periodic with 3D orbitals, and in the impurity, then you have like one effective impurity, one effective atom with those 3D orbitals.
Okay. Thank you.
Okay, thanks. So Lorenzo has another question.
Yes, actually, I have it. It's about double counting. It's quite difficult for me to see what is if there is some risk of double counting in this method, and what is the risk? How do you account for it if you need it?
Okay, so there is no special or additional double counting that you do. So I mean, the extension from the DMFT to the DGAMA is systematic, right? So there you don't count anything double. The double counting is from the DFT, where you start from DFT calculation, right?
Because I might be wrong, I might completely wrong, but at some point you insert some chi, some polarizability, local polarizability. So imagine that you want to take into account quasi-particle corrections, so the polarizability of the system. You add somehow the local contribution twice, or I'm lost in the equation, which is most probable.
Okay, so in the DFT plus DMFT calculation, there is some double counting done always, right? Because you have some part of correlation, local correlation also, which is already there in the DFT, right? Because the DFT is not completely uncorrelated. And this is always done in an approximate, you don't have any good way of doing this, right? Because it's completely different grounds like DFT and which is wave function based, and DMFT, which is diagram based. So actually we don't have any other way of doing additional double counting here in this AbinitioDΓA, but this is maybe something that one would need to think about.
Okay. Okay. Thank you.
Okay, thank you for the questions. Are there any other questions? I don't see any. Last chance. Okay, so thanks again, Anna, for this nice talk.
You're welcome.
Thanks everybody for joining, and hope to see you next month.